Hi, everybody. My name is Srivatsan Vadrajan, and in the next few minutes, I will briefly present our phase one high-level concept of operations and the specific software component, namely the advanced fail-safe functionality that we'll be designing in as part of our Design for Certification project in our course. This is joint work with SRI, Honeywell, and University of Washington, Seattle. As shown in this picture, the high-level system architecture on the top left, we have the ground control system. This is in the ArduPilot terminology, is the MAV proxy ground control system software that talks to the onboard ArduCopter, which is essentially a UAS drone. And the flight software has a built-in flight controls, a whole bunch of modes like takeoff, loiter, land, autopilot, altitude stabilization, etc., which is built on top of existing nav nav sensors like GPS, the iNav, like the IMUs and the accelerometers, and the nav function, which is the extended common filter. The software component that we will be focusing on in phase one is essentially this advanced fail-safe functionality that we have shown here, captured as part of our RADL specification. We essentially have an advanced fail-safe monitor that is going to be monitoring for four different events. We're going to look at the AF geofence breach and essentially for the geofence breach event, and then trigger the appropriate geofence breach recovery action. Similarly, we're going to look at a GPS loss function that is being monitored and triggering a GPS log loss recovery. We are also constantly going to be monitoring for battery, whether the battery, the amount of energy required to complete the mission is sufficient. And if it's insufficient, we are going to trigger an insufficient battery insufficiency recovery action. And also the ground control system loss. If the communication channel between the ArduCopter and the ground control system, if there is a loss, then we would be triggering the GCS com recovery action. For the purpose of our project in phase one, we'll be looking at an onboard advanced fail-safe monitor, essentially talking to the flight software via the same MAVLink interface. So the MAVLink interface is, you can think of these as two adjacent partitions co-located on the same flight hardware, and the transport level interface is via the MAVLink interface. The concept of operations that we're envisioning is essentially an ArduCopter rotorcraft performing autonomous surveillance operation. So the way we envision, you have a launch, the home launch from the home location, you have a waypoint following system. So what we show here is essentially the ArduCopter doing a climb initially via W1, W2, W3, and then descending via W4, W5, and W6, and then returns back to the launch. And the ground control system, you have a couple of rally points that are pre-specified. But we also, during our mission, configure a geofence. And the objective of the mission is to do the surveillance via this waypoint following, but to keep the ArduCopter within the cylindrical geofence defined by the range from the center. Basically, it's a range check of about 500 meters and an altitude check of 150 meters. But we also have a polygon fence within which we want to keep the geofence to be restricted within that safe zone. So these are the 6 high-level events that the advanced fail-safe function is going to be monitoring. So you have the cylindrical geofence, the altitude check, the range check, and then the polygon breach check. So these are all geofence-related breaches. You have the GPS loss being monitored. Then you have the ground control system communication loss, as well as the battery insufficiency monitor. So you have these 6 different events that are being monitored, and the advanced fail-safe function essentially is going to be triggering recovery actions based on these losses. Do note that the mission is essentially an autonomous surveillance operation, so without intervention from the ground control system. So these recovery actions are automatically, by requirements, are baked into the design of the system, and we generate evidences to ensure that the system is safe and is, and the requirements are satisfied. And that is a broad scope of the phase one evidence generation exercise. Just for the exercise, just to go through one of the events, when you have a GPS log loss, Then the recovery action essentially is for the ArduCopter to loiter at the current location. That is, for instance, the ArduCopter may be between waypoints or in transit. So the idea is to loiter at the current location. And if the GPS is recovered, the GPS signal recovers within that 5 seconds, then you can resume the mission and proceed to the next waypoint. But if the recovery does not happen within 5 seconds, then the idea is to go to the last waypoints because presumably this was the last known location. The previous waypoint is there's a high chance that the GPS can, there was a GPS signal available. And so you can essentially, go back to the place where you had the last nav fix via the GPS. And you can coast to that location using only the IMUs and the GPSs, and then land and communicate a landing position to the ground control system. So the way is, this is the top level conceptual functionality that we are going to be encoding with the advanced failsafe function. And we have the recovery actions under the context of these different events that are being monitored. So we will very quickly show the advanced failsafe monitoring function in action in the ArduPilot Citadel environment that is shown on the screen. So on the top left, you have the ground control system MAV proxy. And as you can see, the whole fence has been set up. And you can see on the bottom right is the map with the ArduCopter following a waypoint and within a geofence polygon that has been specified. On the top right, you have essentially the MAV console showing all the initial GPS and everything is perfect. This is the MAV ROS environment, which you can ignore for the purpose of this video. But you can see the advanced failsafe monitoring function that is constantly running on the lower left command line. And so it shows you that the GPS fix, we have essentially now disabled the GPS, and you can see the GPS has been disabled, and you can see the GPS fix loss is now being detected by the advanced failsafe monitoring function, the bottom left. And when you see the GPS being disabled, you can also immediately see the IMUs, onboard the navigation system has stopped aiding the navigation function, and immediately, so there is a problem with that. So you can notice that the monitoring function again has been detected. So once you re-enable the GPS, then you can see the GPS being detected by the advanced failsafe function as being normal. So this is an example of an automatic detection of the GPS loss being monitored by the AFS monitor. We'll give you another example where we have set the altitude check to be around 150 meters, and then we are showing you a scenario where the ArduCopter is essentially climbing to 150, and you can see a geofence breach being detected. So then you can notice the advanced failsafe function automatically also showing that the advanced failsafe monitor has detected a geofence breach. And so once it has reached 200 meters, then we are going to show you a situation where it comes back to normal, and then you can see the situation essentially going to be reverted. So you've reached the 200 meters, and then we are going to continue with the waypoint mission, and then you're going to see the advanced failsafe essentially. We are asking the ArduCopter to follow autonomously the pre-specified waypoints, and so once it falls below altitude 150 meters, you will see the geofence breach being showing that the status is reverted to normal. And that should happen in about, just about maybe 5 seconds from now. All right, so as you can see, the altitude is reaching 150 meters, and then the fences become okay. And then you can see the geofence status breach essentially becoming 0. And then you can see the ArduCopter following the waypoint, the rest of the mission. So that in essence is demonstrating the ability for an independent advanced failsafe monitor to constantly monitoring what's going on board the vehicle for those 6 events, and then taking the appropriate course of action. This concludes the demonstration. Thank you for your attention, and more information can be found in the web link provided below.